looks like it would either way.
Yeah, like act like anything. I mean, you are.
So if you start. Yeah. Okay, if everyone is ready, we'll go ahead and get started to save some time. So today we'll be talking about our project, which we worked with the California Department of Toxic Substances Control and L'Oreal working on non-petroleum based alternatives for nail polish formulations. So I'm Andrea Teneo. I'm a Master Public Health candidate in the Environmental Health Sciences Division with specialization in industrial hygiene.
And hello, my name is Aldo. I'm also an EHS student in industrial hygiene. Hello, OWL people.
Hi, I'm Dominique. I am also an EHS student with the concentration in ergonomics.
Hi everyone, I'm Monique Miller. I'm also an MPH candidate studying industrial hygiene.
Hi, I'm Rita Casera. I'm a senior studying chemical biology with a concentration in computational chemistry and a minor in public policy.
Okay, so briefly, we will cover our background and then move into our strategies, some of our performance criteria and inspiration for those strategies. And then lastly, we'll conclude with some recommendations and leave some time for questions. So moving into our background, nail salon workers are highly exposed to toxic chemicals, including toluene, formaldehyde, dibutyl phthalate, triphenyl phosphate, and many more. And considering this is sort of an untraditional workplace that's not necessarily monitored by OSHA very well, the issue has been overlooked for many years, but in more recent years, many companies and agencies have been looking to take action to remove these harmful chemicals from the market. So for our challenge, our team has partnered again with L'Oreal and the Department of Toxic Substances Control to identify a range of non-petroleum based alternatives and nail polish formulations to eliminate some of these harmful chemicals, especially to reduce worker exposures and consumer exposures alike. And one approach we took for this project is that we're going to look at the entire formulation instead of looking at just one single component. So for the three main components of nail polish formulations, there's the film former, the solvent, and the plasticizer. So the film former makes up most of the formulation and it works to bind all of the components together. So the main one that's used is nitrocellulose at the moment. Then there's the solvent, which works to dissolve the solutes and thin the formula, and it also keeps the formula from drying out. And previously, many solutions use toluene, but people have used more or moved more into using butyl and ethyl acetate. And lastly, the plasticizer softens the film former, making the formula flexible and easy to apply. And dibutyl phthalate, as well as triphenyl phosphate, are the main bad actors that are in current use, but the EU has currently uses DEHT and DINCH as their alternatives, but they're still both phthalates, which have been linked to toxic health endpoints. So moving into our the reason we care about all of this is because of the nail salon workers. So nail salon workers are primarily exposed through methods of inhalation and dermal exposure, and they're primarily immigrant women of reproductive age with low English proficiency. They're often self-employed, they work long hours, and they're often working in poor working conditions with poor ventilation, and they often have limited access to PPE. So they also may have children that accompany them to the salon that may also be exposed. And then if they are pregnant, the unborn fetus will also be exposed. And because of their exposure to these toxic chemicals previously mentioned, they're at risk of adverse health effects, including cancer, reproductive and developmental toxicity, as well as potential endocrine disruption. So moving into our hazard assessments, we conducted a primary hazard assessment for our bad actor chemicals, and to make determinations, we looked to resources, including documents available through the International Agency for Research on Cancer, IARC, FAROS, PubChem, ECHA, which our previous team described well. And then we used the globally harmonized system for classifying chemicals, the GHS documents as well. And then where we couldn't find things, we looked to the literature. So the primary route of exposure to these chemicals is through inhalation, as I mentioned, and highlighted are some of the toxic health endpoints that we were looking at. So toluene is known to cause neurotoxicity, but has also been linked to developmental, reproductive, and respiratory toxicity. Dibutyl phthalate is linked to reproductive and developmental toxicity as well. And then triphenyl phosphate has also been linked to carcinogenicity. And then all of these chemicals have been linked to potential endocrine disruption. Then moving into our secondary bad actors. So these are the ones that are safer than our primary bad actors in use, but they still have some toxic health endpoints. So many formulations have steered away from using the primary bad actor chemicals mentioned in the previous slide and replaced them with these. And while safer, these still pose some health risks, including neurotoxicity, respiratory, developmental, and reproductive toxicity. These substances also still have a lot of remaining data gaps, particularly regarding endocrine activity, which is concerning given our exposed population.
So moving on to our performance criteria. So when you're thinking about nail polish formulations, we're looking for something that is easy to apply, that dries in a reasonable amount of time, and it dries to be glossy, shiny, and hard. We also want something that is going to adhere to the nail, but can also be easily removed with existing nail polish removers as to not damage the nail when you're removing it. And some of the goals or metrics that we had for some of these properties were film forming capacity at room temperature, a certain level of hardness, a pH that's compatible with the human nail, a level of adhesion that is appropriate for nail polish, and a certain level of gloss that was defined by L'Oreal. And sorry, I'm going to go back. There's no way for us to test the entire formulation, but we use some of these metrics to guide our decision in identifying the target properties for each of the components that we decided to focus on. So as Andrea mentioned, the three main components that we're looking at are the film former, solvent, and the plasticizer. As a reminder, the film former is the component that binds everything together when it's dried. The solvent dissolves everything and lowers the viscosity of the final formulation, and the plasticizer is mostly there to increase the flexibility of the film former, which is typically really brittle. So some of the target properties for the film former is something that will form a film at room temperature. And for the solvent, we're looking for something with low volatility, so low vapor pressure, and something that is able to dissolve the film form in the plasticizer that is selected. And for the plasticizer, we're looking for something with a specific molecular weight based on the compatibility with the film former. So the challenge with coming up with the target properties for each of these components is that the target properties really depends on the other components. So depending on the film former, we might have to change the properties for the solvent and plasticizer. So for our strategies, we decided to move forward with looking at each of the components and building out a formulation. So the first one focuses on building out a formulation from Zyne as a film former. And the second one focuses on looking at the solvent and researching water as an alternative solvent. And then the third focuses on bio-based plasticizer drop-in replacements.
Yeah, sure. So based on what Monique was mentioning here, each strategy is focused on starting off with one of those components first. So for our first strategy, as she mentioned, we'll be starting off with Zyne, second with water, and the bio-based plasticizer is component 3. But again, they all depend on each other.
And so moving on to strategy 1, this is the idea of building out a formulation using Zyne as a film former. And so Zyne is actually inspired by the natural product shellac, and shellac is a natural resin. It's secreted by lac insects. So you can see a picture of them right here. Typically they're found in trees in India and Thailand. And shellac comes in a lot of different colors. Some examples are shown over here. Typically, shellac is bleached with sodium hypochlorite prior to being used in nail polish formulations, so that you're starting off with kind of a colorless base. And in terms of the chemical structure of shellac, it is a polymer. And so it's a polyester that has these monomeric units, the single esters. And polymerization takes place through esterification reactions. So you have kind of this carboxylic acid group here reacting with the alcohol group here to form these really nice chains. And overall, shellac has a lot of great properties that kind of help when coming to nail polish. So it is a film former, and so it's responsible for a lot of binding. It also provides a very glossy and shiny finish, which is very important for nail polish, and it's moisturizing, which is important because a lot of formulations, if they're too dry, they end up being kind of they kind of crack later on when they're actually hardened on the nail. And so while shellac is good from a technical performance standpoint, it's a little bit dangerous from a manufacturing standpoint, and there's two main issues associated with it. The first is that during the harvesting process, the lac insects that secrete it are actually killed. And the second big issue with shellac is that the environmental impacts of manufacturing it have been compared to those of silk. And so in general, shellac manufacturing is very pollution driven. And this mainly comes from removing a lot of those residual insolubles in solution. So things like the twigs, the leaves, the cocoons from those lac insects. And so overall, there has been a move to try and find replacements for shellac. And one popular replacement that's come up is Zyne. And so this is the monomeric unit of Zyne. In comparison to shellac, this is a polyamide instead of a polyester, but Zyne contains a lot of the same properties that shellac has, but it's vegan and biodegradable, and we'll talk more about that on the next slide.
Yeah. As Reina described, some of the properties that make Zyne really appealing for our partners is that it's vegan and it's biodegradable. It's non-petroleum based. It's actually based from corn, and it's able to form a film. Additionally, it's hydrophobic, and it's compatible with a lot of different solvents. It also has low water vapor permeability when it becomes a film. But one thing to note here is that depending on the type of Zyne that you use, there are several different forms of Zyne depending on the process that you use. The coloration can range from very clear to a little bit of a yellowish tint, which could be an issue in formulation when you're trying to have vibrant, bright colors.
And so starting off with Zyne as a film former, we then turned into looking at possible plasticizers that we could use for this formulation. And acetyl tributyl citrate has become a more and more popular plasticizer to replace phthalates, so things like DINCH, DHT, which we mentioned before. It's actually used in about 7% of nail polish formulations right now. It's also used in a lot of paints and coatings. And so commercially, industry-wide, people are moving towards this plasticizer. And so Zyne in general is very, very brittle. It is very rigid. But what studies have shown is that tributyl citrate, so that's this molecule right here, but without this acetyl group right here, that Zyne dissolved in 10% tributyl citrate actually forms a very good film that's flexible and it's tough and it can kind of withstand high humidity and water. And so with that in mind, we kind of wanted to look at acetyl tributyl citrate as our plasticizer since it is more available commercially. And we think that it could carry over a lot of the same properties as tributyl citrate. And so now with the film former and plasticizer in hand, we then turn to looking at potential solvents for just one iteration of this sample formulation using Zyne. And for this iteration, our solvent selection was driven by the GSK solvent guide. And so this is a solvent guide basically used for medicinal chemistry, but used by a lot of process chemists. And what's interesting about this guide versus a lot of other similar guides is it does focus on a lot of environmental impacts and a lot of environmental endpoints. And so for this iteration, we chose to focus on optimizing the health hazards. And so we basically focus on these 4 solvents that had the highest health hazard ratings according to the GSK guide, and we'll run you through a more comprehensive hazard assessment on the next slide. Out of these 4 solvents, ethanol and 2-propanol, which are down here, have a lot of literature related to Zyne. So these are actually used to commercially extract Zyne. Zyne can be extracted using 70% ethanol and 88% isopropanol. And so we wanted to look at these solvents more from a hazard perspective to see if they would be safe to continue for this formulation.
Okay, and so due to the lack of transparency from often associated with environmental and health safety criteria, for example, the GSK guide, we further dived into our own hazard assessment. So we rated the chemicals based on sources from the EPA, the European Chemical Agency, IARC, and literature from PubChem. So right here, we can see that Zyme overall is a low hazard with some data gaps in genotoxicity and endocrine activity. And these levels are based on authoritative lists. So the FDA did designate Zyme as a generally regarded as safe chemical when used as a direct human food ingredient. And cancer and reproductive toxicity was rated low by EWG Skin Deep. So acetyl acetate is the alternative chemical we would use in this strategy. When comparing it to the current plasticizers, we can see that they have similar endpoints. There were a few classifications from authoritative lists, so we conducted a literature review on acetyl citrate. Most of the studies we found were looking at health outcomes done on animals. So for carcinogenicity and developmental and reproductive toxicity, there was low hazard found in rat studies. Genotoxicity were low hazards in vitro studies. And then for skin irritation, 59 men and women were tested and no irritation was found. So for eye irritation in rats and rabbits, there was a medium hazard. And then for endocrine activity, an in vitro study, along with predictive tools, also found that endocrine disruption may have not appeared in vivo studies. So when comparing ethanol and isopropanol to the current solvents, we can see that they are slightly less hazardous than the current solvents. So ethanol and isopropanol are volatile compounds. So therefore they can rapidly evaporate at room temperature and have higher concentration indoors compared to outdoors. Some of the health effects include eye, nose, and throat irritation. And we can see that both of the isopropanol and ethanol have a relatively high hazard within that group. And then other effects include headaches, loss of coordination, nausea, damage to liver, kidney, and central nervous system. Both ethanol and isopropanol are suspected of damaging fertility or having adverse effects on the fetus. IARC does classify isopropanol into group 3, meaning that it's not classifiable as to its carcinogenicity to humans. And although this strategy does have a low hazard, overall precautions do need to be taken since there are data gaps within endocrine activities.
And so overall, this is the Zyme-based formulation that we wanted to bring up during this presentation. So once again, we have Zyme as our film former, we have acetyl citrate as our plasticizer, and then we have 2 solvent options, ethanol and isopropanol. And moving forward, we have a few recommendations of how to think about improving the current formulation that we proposed here. The first is considering solvent mixtures, right? So maybe mixing some sort of percentage of ethanol and isopropanol would produce better technical performance. We also talked about how Zyme does turn yellow. Part of this is also caused by oxidation. And so considering adding some sort of antioxidant, maybe if it's a vitamin E, vitamin C, could be beneficial. Also using some sort of blue colored chemical to neutralize the yellow, or a bleaching agent like is commonly used with shellac could be another option. And in terms of other formulations, we also think it could be interesting to use Zyme, but try to build out a few other alternatives for plasticizers and solvents. And so definitely looking into different solubility guides. Pfizer has some, Sanofi has one as well. Other solubility parameters like the Hansen and Hildebrand parameters, and non-alcohols, right? So for this, we definitely focus only on the alcohols, but looking at other hydrophobic solvents that would also dissolve Zyme could be interesting.
So moving on to our second strategy. So the first strategy focused on the film former component, and the second strategy will be looking at the solvent component. So as Andrea mentioned in the introduction, one of the main concerns in nail salons are the emissions from the nail polish. So in this strategy, we'll be looking at the solvent. Again, this is the piece that dissolves the solutes, lowers the viscosity of the final formulation. It can make up to 90% of the weight in the formulation. And traditionally, toluene has been used as a solvent, and companies have transitioned to butyl or ethyl acetate. But we were really curious about looking at water as a potential solvent alternative, because it has no known hazards. So to start our research, we wanted to start really broad by looking at existing formula or water-based formulations that were already on the market. We researched several brands and looked at their full ingredient list to try to identify some film formers and plasticizers that were currently being used. And here we found that a lot of formulations were using acrylates polymer as a film former. So we wanted to move forward with doing a little bit more research there.
And so out of the acrylates polymers, one very common copolymer is the styrene acrylates ammonium methacrylate copolymer. And this has been developed pretty extensively for water-based solutions. And so this copolymer is made up of 3 parts. So you have a styrene, the ammonium methacrylate, and then for the third component, you can either have the acrylic acid or methacrylic acid, or you can have the corresponding ester. Generally speaking, acrylic acid has been linked with a lot of toxicity endpoints, so reproductive toxicity, kidney toxicity, and dermatoxicity. And so we decided to not look further into the acids for now. And one example of a copolymer of this form is Syntran 5620CG, and this was developed by Interpolymer. But it's basically a polymer that was specifically developed for water-based nail enamels. And so in terms of its properties, it has a pH of 7 to 8, which is good. It's within the physiological range. It's not flammable. Again, flammability is at a very, very high temperature. It's also miscible with water. And interestingly, it had 42% solids. And so from the literature for acrylates polymers, generally 40% solids or more is good for having very good plasticizing effects. And so we wanted to look further into this polymer to just see the overall performance from a technical standpoint. And one note I did want to make here is we are focusing on the CG version of Syntran for our solution. This is actually an updated version of the PC polymer, which had an MIT preservative, and this has actually been banned from a lot of cosmetics. So while we focus on CG as our polymer, you'll see that the results in the next slide are actually from the PC version because there's a lot more information on it. And so this graph over here is just showing you the general drying time of a few different formulations. So in orange, we have a solvent-based formulation, and then the other 4 bars correspond to water-based formulation. So obviously, it's very clear that the solvent-based formulation dries very fast, and we'd expect that because there are more compounds that can kind of evaporate into the air faster than water. For the Syntran polymer, that's in this dark blue right here, it was faster drying than some of the competitors that they looked at for water-based brands. Unfortunately, these were undisclosed, so we don't know exactly what was in those formulations, but overall, Syntran still, was slower drying than the solvent-based alternative. And then in this graph, they were looking at the 60-degree specular gloss over time of, again, that solvent-based formulation and then 2 water-based formulations. And the 60-degree specular gloss is basically just a measure of the specular reflectivity of a surface. And so overall, you're hoping to kind of see a stabilization of the measurement over time. And so what you can see for the solvents is once they were dry, basically you had a very, very steady performance. For the water-based formulas, there was kind of a dip in performance. And this is mainly due to, again, the way that they dry. So water-based formulations tend to dry from the top down. Solvent-based formulations tend to dry from the bottom up. And so overall, for water-based formulations, you have to wait longer to get that consistent performance. But Syntran in general seemed to outperform the competitor solvent brand that they were looking at. And so it does seem promising, at least looking at it more long-term.
So we also conducted a hazard assessment for all the acrylates Raina just talked about. We used IARC, EPA, ASTDR, and ECA as well. So for styrene, its acute exposure was the mucous membrane and eye irritant, along with some gastrointestinal effects. Its chronic exposure was the central nervous system, some hearing loss, and peripheral neuropathy. Thank you. And then its reproductive and developmental effects. There wasn't really an increase in developmental effects, but there was an increase in spontaneous abortions and also a decrease in sperm concentration. And then for its carcinogenicity, it was in group 2B. And then for methacrylate ester, its acute exposure was skin, eye, and nose irritant as well. And then chronic exposure included development of skin allergy, which was an itch and a skin rash. And there was data gaps within reproductive and developmental effects, and it was not classifiable to cause cancer. And for ammonium methacrylate copolymer, it was also a skin and eye irritant for both acute and chronic exposure, and the reproductive effects, there was data gaps as well, and it was not classifiable to cause cancer.
And so generally speaking, then the acrylates, although they have good technical performance from an actual health hazard standpoint, they don't seem to be that great. And so we wanted to also consider some natural film formers that could potentially be looked at further by our partners. And the real criteria here was that they would dissolve well in water. And so toluene is a natural film former that's often found in like edible films. So breath strips, for example, it's actually 100% based off of vegetables. So again, very vegan, a very clean ingredient. And this ingredient has actually been used to create a lot of cosmetic masks recently, so a lot of peel-off masks, and it's been shown to have a dry time of about 10 to 15 minutes. So for nail polish especially, this could definitely be a promising film former to look into. Another interesting class of kind of natural film formers are the alginates. And so this is an example of sodium alginate, but alginates are generally, they come from kind of the marine algae, the cell walls of them. And so while alginic acid is not water soluble, the salts are water soluble. So sodium alginate, for example, is water soluble. And these, similarly to the toluene, have been used in like clay masks for cosmetics. So it could be another interesting area to look into. And finally, chitosan is another really popular film former. It comes from chitin. And it's actually been used in a lot of topical nail lacquers. And so in order to kind of treat like nail fungus, they've used this as a film former. And so these are kind of 3 areas we'd recommend exploring further.
So generally speaking, water is a great solvent for nail polish formulations, but there are some issues that arise given the drying time. As was previously mentioned, nail polish generally dries from up down instead of from within out. So there also are some issues with the nail polish becoming wet again. Let's say you're in the shower and it absorbs that water, which will introduce some issues with bacterial growth. But these are issues that can be mitigated in a professional setting, such as a nail polish salon, using a fan, and the nail worker will probably be able to apply some sort of antibacterial to the nails and follow those instructions accordingly. And yeah, so we'll move ahead to future directions.
And yeah, just in terms of some future directions. So obviously with the acrylates, the copolymers, we're dealing with a lot of toxicity. And so considering some other film formers for water would be interesting, especially those natural film formers that we brought up on the last slide. A few remaining questions that we have also are, we kind of want to look into how plasticizers work with the acrylates. We're not exactly sure how this in would function in solution. A lot of these formulas are proprietary, and so there's really not a lot of research. And so ideally someone in a wet lab could test this out. And finally, we do want to understand how kind of those water-based properties of cosmetics actually apply to nails, right? So we talked a lot about peel-off masks, how transferable are properties that are kind of relying on skin to the nail bed.
And now moving on to strategy 3, we decided to use a bio-based plasticizer drop-in replacement. So how it was mentioned before, plasticizers are used to increase flexibility by softening the film former. And then the red ones are our current bad actors, and then the ones next to it would be the safe alternatives that are currently in use. So to move away from phthalates, companies are developing alternative plasticizers, and these are some alternative plasticizers that L'Oreal has developed and patented in the past years. So all of these plasticizers can be used alone or combined with other plasticizers. So for epoxidized oils, they do have low viscosity and high dry extract. L'Oreal specifically used the Vernona oils that are derived from the plant ironweed. Sulfonamides have a high hardness film, which makes it a better resistant to wear. And overall, they have a good and shiny appearance. But it is a sulfur, so you can experience some possible peeling or irritation to the skin. The cross-linked polyester fluorinated citrates do have a stable composition that produce a flexible and glossy film, which allows the formulation of a non-occlusive film.
And so while some of those kind of plasticizers on the previous slide are interesting, obviously we do want to stay away from sulfur and fluorinated compounds where we can. And so we were able to come across natural carbonates as another alternative for bio-based plasticizers that have actually been more commonly used as drop-in replacements. And so the good thing about carbonates is you can put them in your formulation and you don't have to change many other parts of your formulation. So that would be definitely beneficial from an industry standpoint. And so carbonates in general, you're looking at this sort of a generic structure. The R1 and R2 alkyl groups are usually equivalent for the carbonates that have been explored for nail polish. And generally speaking, they, at least so far for nail polishes that they've been explored in, they form a stable composition, they form a good kind of flexible film with the film former, and then they also form that glossy finish. And so from a property standpoint, it seems pretty promising. 3 carbonates have been explored pretty in depth so far. So diisoamyl carbonate, dilauryl carbonate, and glycerol carbonate. And we'll kind of compare some of the properties of all 3. Glycerol carbonate, though, in general, has been talked about a lot more because of the way that it can be synthesized in a bio-based manner. And so we'll focus a little more on glycerol carbonate than the other 2. And so just the kind of overall technical properties of glycerol carbonate, definitely chemically very stable. So thinking from a shelf life perspective, you don't want your nail polish to go bad in 6 months. And so this is definitely promising, non-flammable, water soluble, and also biodegradable. So at least from kind of the green chemistry standpoint that we're looking at, seems like a good molecule. And so in this experiment, they basically looked into the hardness of the films using different plasticizers. And this is with those 3 carbonates we talked about on the previous slide, as well as acetyl tributyl citrate, which, if you remember, is used in about 7% of nail polishes right now. And they kind of compared that performance of hardness to no plasticizer. And this is the formulation that they used in case you're interested. So again, just swapping out the plasticizer of interest. And so the test that was carried out here is the Persos hardness test. And it's basically a pendulum test that measures the oscillations of the pendulum to figure out how much it is dampened by, whatever film you're looking at. So it's typically run on like a dry film. And overall, what they found is that for no plasticizer, which is down here, there was no dampening of the pendulum. For glycerol carbonate, which is the line up here, there was a lot of dampening. And so that meant that glycerol carbonate had higher plasticizing properties than no plasticizer, which is good. That is as expected. Interestingly, dilauryl and diisoamyl carbonate, which are these 2 lines in the middle, had moderate plasticizing effects. And glycerol carbonate did seem to outperform acetyl tributyl citrate, which is right here. So it's pretty promising that it's performing kind of one of those commercially used plasticizers. And so just to consider how glycerol carbonate can be made, this is a schematic of a lot of different synthetic pathways that are used. This pathway in particular is of a lot of interest from a bio-based kind of standpoint. And so glycerol carbonate can basically be synthesized from glycerol, which is the alcohol, and DMC, which is dimethyl carbonate. And there's 2 options for the catalyst. You could use potassium carbonate, sodium carbonate, and there's kind of been literature on both. But overall, this transcarbonation basically is relying on bio-based reagents, which is good. It's also very high yield, high selectivity for the actual product. And generally speaking, uses very mild reaction conditions. It's also very easy to separate out the glycerol carbonate at the end. And so this is definitely a good bio-based method to create glycerol carbonate. For the other carbonates we talked about, if you just replace this alcohol with a different alcohol, you can actually make those as well using the same scheme. And so with an understanding that glycerol carbonate can be synthesized and also has good properties, we just wanted to consider how it would react with the existing film former in nail polish, which is nitrocellulose. And so in this schematic, this is a proposed schematic from a paper, but the black is the nitrocellulose, so that's the film former. And then the blue is the glycerol carbonate, which is our proposed plasticizer. So you can see here, like these hydroxy groups from the glycerol carbonate react with hydrogen bonds with kind of the nitro groups off of the nitrocellulose. And this kind of forms a very stable and ordered chain of the nitrocellulose and the glycerol carbonate. And interestingly, the glycerol carbonate kind of helps to keep the nitrocellulose like well spaced out. So there's enough volume in between, and that leads to a high plasticizing effect. And so this paper actually found that if you reduce glycerol carbonate below 10% of the total formulation, you can still meet the criteria of nail polish. And so that's less than kind of most of the commercial plasticizers are nowadays.
So in this hazard table, we're comparing the 3 previously mentioned carbonates to acetyltributyl citrate. I'll be calling ATBC. It's clear that many data gaps exist in our endpoints of interest for the carbonate plasticizers. So research shows that ATBC, as was already mentioned, is low hazard for carcinogenicity, mutagenicity, developmental and reproductive toxicity, based on literature searches, because there wasn't very much there for authoritative lists. And in this case, however, literature review was done for diacetyl carbonate, and developmental reproductive toxicity was found as a moderate hazard. And if you direct your attention to the center of the table towards skin and eye irritation, you see that there's a steep increase in that endpoint of interest. Comparing the diluryl and glycerol carbonate compared to ATBC. And data gaps appear across the board for the carbonates in general. And our preferred plasticizer for this strategy, glycerol carbonate, is also a moderate systemic toxicant, both from single exposure affecting the respiratory system and repeated oral exposure affecting the kidneys. So clearly there's room for improvement and for future research. And let's see.
And so from a technical performance standpoint, then overall, natural carbonates definitely seem like a promising alternative for drop-in plasticizers. They can be synthesized in a variety of different ways. And glycerol carbonate does outperform kind of one of the leading commercial plasticizers to replace phthalates. And so that's good. In terms of future directions, we definitely want to recommend looking into kind of other glycerol esters. So we looked into carbonates. There's a whole lot of other esters that have been developed in a lot of different patents. So those could be interesting as well. Also, there are related classes to carbonates. So diols, glycols, for example, could emulate a lot of the technical performance that we talked about, but might be safer from a health hazard standpoint. And then we also want to look into kind of non-glycerol related substances. So a lot of other classes as well came up during our research from different patents that we'd recommend looking into.
In contrast to Raina's points, ATBC absolutely outperformed glycerol carbonate when it comes to the hazard endpoints. And as noted in the previous slide, glycerol carbonate was reported to ECHA with moderate levels of acute and systemic toxicity, and there was literature also corroborating that information with rat experiments. And given all the data gaps, which was asked in the previous presentation, we felt uncomfortable with that. So we took a step further and ran some predictive tools, and the structure of glycerol carbonate was found to possibly cause some toxicity. So given that that predictive tools outcomes, our future direction holds a strong preference for ATBC as our plasticizer. And as you remember, ATBC was used in our first strategy.
So now we're going to move into some of our recommendations. So given that we were examining the whole formulation, it wasn't really feasible for us to look or directly compare our strategies based on their technical performance. So instead, we've developed sort of a pros and cons table to choose which strategy to sort of move forward with. So starting with our Zyne strategy, Zyne poses few known toxic health endpoints, and this strategy would bring a new approach to market. It's hydrophobic and flexible, so it would give it good potential for easy application to the nail. It's also vegan and biodegradable, which can make it an attractive product to the clean beauty market. And but some concerns with Zyne is that it still needs to be removed with some type of alcohol, and it also remains a skin and eye irritant. So some of our remaining questions with Zyne revolve around revolve around using antioxidants to prevent color change. Again, our partner mentioned that it already has a yellow hue and it can oxidize and turn even more yellow. So using some type of pigment, blue pigment, to cancel out those yellows is something that we were looking at. Next, moving to our water strategy. Some positives with this is that it's easily removed and it has no known toxic health endpoints. But it does require some type of it will require some type of additives considering the potential for bacterial growth. And then we looked at some customer reviews, and some people were pretty not pleased with the drying time and the instructions for application. So that's something that we're going to have to consider moving forward. But it does overall reduce the need for hazard communication to the workers. So that's a positive thing. And it's pretty inexpensive and we can use soy-based removers there. So some of our remaining questions with water is its ability to suspend pigments, and then what additives are compatible with these types of formulations. As we mentioned, those will be necessary. And then lastly, our third approach can be synthesized in several ways, including one that is bio-based. And this method has a pretty good amount of research on the compatibility between the components. So that's helpful for our partner moving forward and deciding like what the total formulation will look like. However, there's still a lot of data gaps regarding the health endpoints of our proposed plasticizers. So it's going to require a lot of additional testing before use. One of our remaining questions here is how we classify compounds that are both plasticizers and film formers, and how much of the formulation can they actually take up to be successful. So finally, moving into our final recommendations, the Zyme strategy overall brings a new approach to market that can achieve similar results to shellac formulations, but is vegan. Water-based formulations may not achieve similar results to current formulations without proper application and care. So again, we saw some of those customer reviews reporting dissatisfaction with those type of formulas. So additives are definitely something to consider in this area, considering bacterial growth. And then lastly, our alternative plasticizers. It will definitely be beneficial for the industry overall to look into, since generally cosmetics are shifting away from using phthalates in their formulations, but it's going to require a lot more research and testing to be considered safer than what's currently, or what we described in our other strategies. So in the end, all of our strategies eliminate the bad actors, but the Zyme-based formulation offers a new and inexpensive approach to create vegan, clean beauty nail polishes. That's my presentation. Thank you.
Question from the room, and then if you're on Zoom, you can raise your hand or ask them to the chat. Not a question so much, but just sort of expressing appreciation. I've been working in this area for 15 years. I did some of the early analysis that identified the toxic material along with other folks, and we watched the regrettable substitutions happen. So I'm just really, really appreciative of the systemic approach to this, and really great to innovative work with the California helping out a lot of collaborators. And so thank you on behalf of the workers for doing this work.
Yeah, and the
We try to speed up the drying time with such water-based products. I assume you could either use moving air or you can use a hair dryer on the boat. And how much can you speed up the drying time, and what would this affect the appearance by speeding up the drying time?
So definitely fans are one thing we talked about, is how can those be used? The main issue with water-based is, again, how it's drying. So the top of the film is drying first and then the inside. So even with fans, you can definitely help to solidify the outside, but you're still stuck with kind of that middle wet surface. And so a lot of the formulas that are on the market right now, they suggested having like a 6-hour curing time overnight. So basically, if they're at home kits, at least like apply them, let them dry to the point where they're not wet to the touch, and then let it cure for 6 hours. And so we're still figuring out how to dry the inside. I think that's definitely like one very big question for this whole market.
Thanks again, a very interesting talk. And again, highlighting the complexity of having that. I think the method of application and drying being limiting to your formulation water, right? It doesn't have water base, which is in theory latex in coating community, right? So what did you find on really high solid latex, for example, on really high solid? Because it seems like, you know, the drying a water-based solution as we experienced already takes more time because water, the concentration pressure of water is just lower than organic solids, right? It's just harder, right? Drying water. So higher solid content. Did you look any into that? That where they go about 60% solid content instead of the 40 that you mentioned? Did you look into that somewhat? Or?
Yeah, so that's a good question. Since we couldn't make the formulations, it was definitely hard to kind of play around with the solid. But if you remember, we had a slide at the beginning showing kind of the overall breakdown of what solutions look like. I think it was like, and it had kind of the percent mass, but typically with the plasticizer, I think you can go towards like that 60% as well. And so
I can't find them.
yeah, we couldn't find, most of the literature doesn't tell you how much the solid percentage is. So even with Syntran, we're still not exactly sure what the solid percentage was in the whole formulation. We just know what it was for that polymer.
Sorry, technical difficulties. Can't find the mouse.
Did we find it? It's right here.
There it is. No, like there, this doesn't work.
Oh,
I know.
yeah.
I think, you know, when you look at some of those, they're called high solid. I can't remember the short, but they go up to 60-70% formulation. I think, you know, you don't want to use that polymer you're saying. It's super interesting to see like how you talk about seeing and like high solid content, water-based systems. Yeah, I like that something.
I have a couple of comments and questions on here. One, just in response to that question, Ron Zoom mentioned that higher solid levels also will cause chipping faster, so maybe that's
Okay, that's one of our partners.
Red
by
is,
the
yeah,
way.
he's from L'Oreal. Yeah.
Yeah, and then there was a question earlier, which you ended up kind of answering, but I'll repeat it anyway from Marty. This is a great presentation. Is that used in any nail polish formulation currently? And then you kind of touched on this in a different aspect, but is that soluble in carbonate solvents?
Yeah, so I don't believe it's used in nail polish formulations right now. Shellac has been used, but just again, because of the way it's manufactured, most formulations don't rely on it. Zion though has been used to replace shellac in like a lot of other types of products. So it's definitely, there's like extensive literature showing its like film forming capabilities and especially comparing it to shellac. And it's also food safe, for example. So
Yeah,
we
it's
found-
used in like pill like casings, so that like because of that, that was like one of the reasons we felt pretty good moving forward with it. It's like our philosophy was like, if you can eat it, it's probably fine on your nail, you know. So yeah.
Just going, have you read try to draw the water out?
And something. Yeah, that could be an interesting approach. It's not something we had time to look into, but I mean, anything to keep to help it dry, right? More and more places are starting to come up with these water-based formulations, and yeah, the online reviews were like, it takes so long, my thing smudged, you know, so.
I have a question about like skin. So you guys mentioned like nail polish, and there's like so many ways you can do it. So
Yeah.
I'm wondering if you guys like it was a side. You look at like regular nail polish because the limit is still, or like, does like regular polish like in like have the most like hazard associated with it, or did you guys like consider looking at different options like stick ons and like do it?
So with like looking at regular nail polishes as opposed to like gel or other things like that, it was more in like the interest of our partner. And I think generally speaking, all the other types that like require curing in the nail salon are more toxic. So that's like another health thing in it on its own. But for the peeling or the peel off nail polishes, that actually did come up as like one of our potential strategies. But the issue with for a lot of water-based nail polishes are actually marketed as peel off nail polishes, but this just kind of means that the performance is not great if it peels off. So But
also found
as
to be-
adhesives, like that was something that we thought about, but we, since that just basically is dropping in a sticker on your nail, we didn't think it was like super helpful for our partners, so.
And our partner also brought up that peel off nail polish can be damaging to the nail.
Yeah, it can
But
peel off like the top layer of your nail. I don't know if you've ever peeled off your gel. I've done that and it's not good for you,
but
so.
something to consider there. Do we have a higher priority of less toxicity in the nail polish with the damaged nail? Or what? So it's dependent on if you care about your nail health or
Yeah,
Yeah, and I think
other
there's,
health.
I think there's also like a marketing component, by saying it's like peelable, they often market it to like kids as like a non-toxic alternative that you can peel off without some kind of like remover. But again, yeah, there's the issue about it potentially damaging your nail.
Are like the nail polish you were looking at, like, are those considered to be like less hazardous than these other nail polishes that have like application like dip and gel? Is that?
So it depends. So just in general, so with gelinol, you're also dealing with things like UV. And so that definitely changes the overall properties. Acrylics, for example, we talked a lot about acrylates. So acrylic nails do rely on acrylates a lot of times. And so that's definitely another big area of concern. MMA is sometimes used to even like remove acrylics, and that's a very, very dangerous polymer. And so it kind of ended up being like a very big scope, but like a lot of the chemicals we did talk about here are present in those formulas as well.
any more questions online or anything? Oh, one more. Yeah.
So what's your concluding, remember, reducible acetate versus, because you talked about toluene
Mhm.
as being common in formulation, but did you conclude that reducible acetate was as a solvent would be a improvement if you increase or, and is that like the solve?
It's definitely safer than toluene. So like, even though it had some like health endpoints that we were concerned with, like if you were to choose between the two, we would definitely go with what they're currently using. So the ethyl and butyl acetate.
But we wanted to take a step forward and see if are there any other options opposed to butyl acetate,
Right.
Which is how we arrived to ATBC.
Toluene has basically been phased out at
Yeah.
this point, more or less. So most of the formulation, well, yeah, not completely. There are
supposed to be.
a lot of
phased
studies
out.
where they kind of find trace amounts of stuff they shouldn't be finding in formulations. And obviously some salons have like very, very old bottles, which is kind of an issue, but
Yeah.
Generally, safer formulations have been acetate, butyl acetate and plastic.
Yeah.
It's definitely an improvement.
Yeah.
Absolutely. All right, I think we should break. Really nice job.